Energies of solution formation. Remember our really general solubility rule. Like dissolves like. That means that if our solvent is polar, then it will dissolve polar or ionic solutes. And if our solvent is nonpolar, it'll dissolve nonpolar solutes. So let's talk about how a solution is formed. There are basically 3 steps involved. In our first step, the solute particles are going to have to break apart into individual components. So in other words, we're going to have to expand our solute. And that typically requires energy because we're breaking intermolecular forces. The second step involves our solvent. And again, we're going to have to expand the solvent by adding energy in to overcome the intermolecular forces in the solvent. That way, there'll be room between the solvent particles for the solute particles. And our third step occurs when the solute and the solvent particles interact with each other to form a solution. And in this case, since we're making intermolecular forces, we're going to be giving off energy. So if we look at the energy overall, we have to add energy in to get the solute prepared. We have to add energy in to get the solvent prepared. And then, depending on the interaction between the solute and the solvent particles, we're going to form a solution. And by adding those 3 energies together, that would give us the overall energy for forming the solution from its individual components. So let's look at a couple of examples, but we're going to use no numbers. We're just going to kind of use some logic. Our first example is going to deal with mixing oil and water together, and we're going to think about the 3 steps that must occur in order for us to make a solution. Well, the first step is going to involve the solute particles, which in this case is the oil. Oils are pretty nonpolar, so they're held together by London dispersion forces primarily. And we know that London dispersion forces are fairly weak forces, so we're not going to have to add in a whole lot of energy to get the solute particles ready for the solution. In our second step, we're going to have to take those water molecules and we're going to have to expand them in order to allow the solute particles to fit in. And we know that water molecules are held together by strong hydrogen bonding. So that's going to require a large amount of energy added in order to get the water particles ready to dissolve the oil. And then our third part has to do with how the oil and the water particles interact with each other. And we know that nonpolar and polar don't typically mix together. They barely interact at all. So we're not going to have much in the way of energy given back when the solute and the solvent particles interact. So if we think about adding those 3 energies together, we have to add a little bit of energy in for delta H1. We have to add in a lot of energy for delta H2, and maybe we get back a tiny bit of energy for delta 3, but what that's going to give us is an overall enthalpy of solution that's large and positive. So will a solution form? No. Well, we know that oil and water don't mix together to form a solution, and the reason is too much energy has to be added in order for this process to take place. So let's look at another example. Let's say we want to talk about salt and water. And we're going to look at each of the 3 steps again. So we've got our delta H for the first step, which means we want to take the sodium chloride particles and we want to break them apart into their ions. Well, we know that they're held together by strong ionic bonds, so we're going to have to add in a lot of energy in order to break those forces. Okay, the second step involving the solvent. Our solvent is water. We've got those strong hydrogen bonds, so again, we're going to have to add in a lot of energy in order for our solvent to be prepared for the solution. Now we want to talk about the solute and the solvent particles interacting with each other in our third step. And there's a lot of interaction between the sodium ions in water and the chloride ions in water. So we're going to get a lot of energy back. And again, remember that a positive means an endothermic process and a negative means an exothermic process. So now let's look at our overall process. Well, delta H1 is going to be positive and pretty big. Delta H2 is going to be positive and pretty big. Delta H3 is going to be negative and pretty big. Now overall, the delta H for our solution is going to be a little bit positive, but it's going to be very small. So we're not going to need a whole lot of energy overall in order for us to dissolve sodium chloride in water, not nearly as much as the energy we would have had to put in order to get oil to dissolve in water. Okay, so will a solution form? Yes, well, we know that salt dissolves in water. But we had to add energy in. Why would a system occur if we have to add energy in? And the reason for that is when the sodium chloride dissolves in water, the sodium ions and the chloride ions separate from each other and disperse uniformly throughout the water. And nature tends to favor disorder. And sodium and chloride ions separate are much more disordered than they were when they were together.